Well, our topic for today is electrical safety testing, back to the basics, because it is a refresher. We do each need to refresh ourselves from time to time on all the topics for medical device quality assurance testing. And electrical safety is also one of those. These standards do evolve, and so they change, although slowly. So we're just going to give everybody a chance to go through some of the following things. Why electrical safety testing is still important to reduce the risk of injury or death to patients, and what has changed in the international electrical safety standards. And then we'll teach you some tips and tricks about electrical safety and use of our test equipment. So we're going to start off with a poll question. And the question is, which kind of electrical shock is not felt? Is it microshock or is it macroshock? Edna, would you launch the poll?
Absolutely, Jerry. And that first poll question has been launched. And we will give participants about 30 seconds to enter their responses. Thank you, everyone, for participating in our first poll question. Responses are coming in. And Jerry, I know this is one of your favorite topics and one of your favorite questions that you like to engage the audience in. So,
Indeed,
yeah,
indeed it is.
absolutely. All righty, so I'm going to go ahead and close the poll question now, and I'm going to share the results. So 79% indicated microshock, 21% macroshock.
Well, very good. In fact, the correct response on this one is microshock. A microshock is defined as current that is flowing through a human being's body that they probably don't feel. Macroshock is definitely much bigger, and you will feel that. So let's take a look at some of the thresholds of shock. So you can see in this slide, and especially in the colorful kind of bar chart on the right, we have from 1 to 10 milliamperes, we get a mild shock. You can feel that. And this may be a trip setting for a ground fault circuit or a ground fault interrupter. A little bit beyond that, we begin to get muscle contractions, and the victim can no longer let go of the wire containing the current flow. Severe shock will mean breathing is difficult or impossible, and that's because your diaphragm is now fully contracted and is not moving. It's just contracted, and so now you can't breathe. From 20 to 50 milliamperes, the heart stops pumping, and as you go higher, you get increasing probability of death. So what we're talking about is enough current to light a 100-watt light bulb. No more than that can be fatal. So you do need to be careful around electricity. You need to be careful if you're repairing things like especially power supply circuits or some other big display circuits and things like that. So please do be careful about shock. Now I have another poll question for you. This has to do with how often you perform electrical safety tests on all your electromedical devices. So we want to know, do you in your hospital or where you work perform electrical safety tests? And by tests, I mean measurements on electromedical devices at least once per year or annually. Yes, no, or I don't know. Good job, Edna. You're launching the poll for me.
Yep, you got it, Jerry. And so we will give participants about 45 seconds to enter their response. And once again, thanks to the audience for participating in our second poll question
Mhm.
today.
We typically have a lot of students, and so that I don't know may be a valid question, a valid response for them because they may not have had any experience. But for the rest of the biomeds that are actually working, we would like to, it's going to be interesting to see what we see.
Okay, wonderful. All right, Jerry, I'm going to go ahead and close that poll question and I'll share the results. 82% indicated yes, 12% indicated no, and additional 6% indicated I don't know.
Okay. So mostly we would say for the scheduled electrical safety testing, we would do that one time per year for every electromedical device, anything that plugs into the wall or is powered by electricity of any kind. However, that also tends to ignore the fact that we're going to do electrical safety measurements on incoming inspection, or also called acceptance testing. And there's two times that kind of situation happens. When a medical device is brand new, before you put it into clinical use, you need to do the acceptance testing, and that will include electrical safety measurements. The second situation that includes incoming inspection is if you sent the medical device away from your hospital or facility for someone else to repair and it came back. When it comes back, you need to do another acceptance test, including electrical safety measurements. So acceptance testing is not included in this annual go round. Also, anytime you do a repair on a medical device yourself in-house, then you also need to do another electrical safety test and with measurements to make sure that you have returned that medical device to being safe and effective for clinical use. Thank you for your responses. Safety is the key for electromedical devices. That can include all kinds of things: hospital beds, surrounding environment things, ECG leads, transesophageal echocardiographic probes, TEE, and many, many other things. So electrical safety becomes a very important part of the testing we do. And it doesn't have to take a long time, depending on the international standard that your facility and your country even may be working with. So let's take a look at when we do electrical safety measurements. I already talked about acceptance testing. That's number 3 on the check boxes. Design validation testing, type testing means the same thing and this happens at the medical device manufacturer. When they are finished designing and they think that they have the product ready, the medical device ready, they will do validation testing that needs to include the electrical safety measurements in accordance with the appropriate standard. And we'll talk about that in a minute. And then for the rest of us, besides acceptance testing, there's our routine testing. That's the once per year we just talked about. And then after service, that means repair, we're going to do measurements again. So here are the standards underneath the big umbrella called IEC 60601. That is the umbrella. So please, if you're talking about the standards specifically, you need to use the standards name specifically. Say what you mean, don't shortcut it. So in this case, the international standards are the IEC, the International Electrotechnical Committee, and that is IEC 60601-1. And this standard is written for the manufacturer of the medical device, to use in their design type testing, and they may also use it for their final assembly test in the factory. And that would be a very appropriate thing to do, because it's in the factory, the final assembly is the first time that all of the pieces, parts, and sub-assemblies have been pulled together into one complete medical device. And then it's definitely appropriate to run the test in accordance with the IEC 60601-1. They may be used for acceptance testing by hospitals and other facilities, but there's also a shorter test that can be done that should be sufficient. The next standard underneath the umbrella, having to do with electrical safety, is the IEC 62353. So for all of you out here in Asia Pacific, ignore the NFPA 99. That is a US only code. It's not a standard. And these, the IEC 62353 is designed for use in recurring testing. That is every year, after each repair, and the next and the next. And that's because it has been specifically designed so that it does not shorten the useful life of the medical device. The IEC 60601-1 does or may. So keep that in mind. IEC 61010, I want to just cover here, is specifically for clinical laboratory equipment. And it is for the manufacturer and their installer to perform. There's 2 tests that are required under this standard. Those need to be done by the manufacturer or the installer before they turn that part of the laboratory over for go live, for readiness for use by the hospital. So after that installation and that go live of the clinical laboratory equipment, then we will use the IEC 62353 ever after, until we install some new clinical laboratory equipment and get the handoff. That's what we'll do. So you'll get a lot of pressure and a lot of people who believe that the IEC 61010 tests need to be done every year and scheduled for that clinical laboratory equipment. That's not true. IEC 62353 after the installation has been turned over. All right, why should you use IEC standards? This is another poll question, and I want you to, in this case, check all that are correct, that you feel are correct. So that would be the IEC standards are tried and true. The IEC standards are created by experts from medicine, academia, and industry. The IEC standards evolve with revisions regularly. So, Edna, would you launch the poll, and let's see how many of these choices each of our participants feels is important.
Okay, and that poll question has been launched.
And remember, our question is, why should you use the IEC standards?
Responses are coming in. And Jerry, for this one, we'll give them about another 30 seconds to enter their reply. Okay. Once again, thanks to all attendees for participating in today's webinar, as well as our poll questions. Very helpful for us as we plan future webinars. And so I'm going to go ahead and close the poll question, Jerry. Share the results. All right, 50% indicated the IEC standards are tried and true. 69% indicated the IEC standards are created by experts from medicine, and 54% indicated the IEC standards evolve with revisions regularly.
Well, very good. And the best response is all three are reasons why you should use the IEC standards. And I should say, acknowledge that some countries produce their own local national standards that use the IEC standards, but then make them maybe make them a little bit tighter in terms of pass-fail criteria or things like that. China is one of those countries that do that. Australia and New Zealand are countries that also have their own local national standards, but they track very well and have the same requirements, same or very similar requirements as the IEC standards have. And therefore, they are always a good place to start. And they're a good place to start even if your country has not adopted or created any electrical safety or minimum performance and safety standards. No one ever got fired for following an international standard, but you should write a policy that says until our country has a standards of its own, we will follow IEC standards for minimum performance and safety, including electrical safety. And that will help a lot. The next statement that is also important is we will follow the manufacturer's service manual test procedure whenever we can obtain it, whenever we can get it. Because we know that out in Asia Pacific in particular, it is often very difficult even to get the service manual test procedure for a particular brand and model of medical device, unless one or more of the people in your facility go to the service school from the manufacturer of that medical device. That may not always be economically available to you. It certainly is going to mean you're going to have to go out of your country, and typically it will mean you need to understand a language other than the language you speak every day. So we realize that some of those things happen, but the international standards are really good and they're a safe place to be, and they really do help us make sure our patients are really kept safe. All right, so who should use the IEC 60601-1? I've already told you, it's written for the medical device manufacturer in their design validation testing and their final assembly testing in the factory. This one can be used by hospitals for acceptance testing. However, 62353 is also sufficient, and we'll talk about that in a minute. So some countries adopted the IEC 60601-1, but then didn't provide any other standard for use by the hospitals. And therefore, and this happened in Western Europe, in many countries in Western Europe. And so now in Asia Pacific, we see sometimes that happening as well. Remember that this standard has a couple of tests that would tend to shorten the useful life of the medical device. They're perfectly appropriate for design validation testing, and they're perfectly appropriate for final assembly testing, but we don't want to shorten the useful life of the medical device in the hospital, or clinic, or wherever we find it. So for that reason, there's another standard that gets used. Oh, well, let me first talk about a couple of things that changed from the second edition of the IEC 60601-1 to the third edition. We have a test called touch current. And touch current was previously known as enclosure or chassis leakage current. So if you've been around for a while, you may be familiar with the older terms, the older names for this test, but all these names mean the same thing. It's called touch current now for a reason. The requirements are unchanged. your test point is not the accessible ground pin on the medical device. It is a conductive uh, connection that is not grounded. A conductive test point that is not grounded. Well, that's fine, except almost all of the newer medical devices are completely plastic. There is no conductive test point aside from the protective earth test point on the back or on the device. So what do you do when there isn't any test point? You just ignore the test? No, you can't. In fact, this test is the one test that must always be done, no matter what. And so if it has to be done, the Standards Committee also has provided guidance for us to figure out how to create a test point for this particular test. Remember that this test point is a conductive, non-grounded or non-earthed point within the reach of the patient or of the nurse or doctor who might touch the medical device and touch the patient at the same time. So this last week, I was teaching our tech support team about this particular test, and I had them practice running it. And so you can see a patient monitor there with aluminum foil that has been taped down to the front surface of that particular patient monitor, because that's where the patient or the nurse or the doctor could easily touch it and then be touching the patient. And so here's how that current is going to flow and why we use aluminum foil. In electronics, a component that has a conductor, an insulator, and another conductor all in that one component is called a capacitor. A capacitor will carry current flow. And so what we have formed when we have inside this plastic shrouded medical device is conductors and current flow inside of it. And we as human beings are conductors. Yes, we are conductors, not insulators. And therefore, the plastic being an insulator, when we put our hand on the outside of that medical device, current will flow, and we need to know how much, under what conditions, and where is it flowing. That's the questions we need to answer. And so by putting this aluminum foil on the outside, we have completed that capacitor. Current flow and conductors inside, the plastic is the insulator, and then the aluminum foil is the conductor on the outside. We clip our test lead to that, and voila, we make the correct measurement, and we are able to identify what is the worst case, that means the biggest leakage current available, whether it's power on, power off, normal or reverse polarity, or when we run the single fault conditions called open neutral or open ground. Okay, aluminum foil about a 10 centimeter square, 2 or 3 thicknesses, and wrap the edges together and then tape it down, just as you see in the picture here. And this test, as I said, must always be done regardless of the class of the medical device, regardless of whether we have a ground pin or no ground pin. It still has to be done, this test, the touch current test. And it's called touch current because the patient is touching the medical device, or the nurse or the doctor is touching the medical device and touching the patient. All right, so who should use the IEC 62353? This standard originated in Austria as the Austrian VDE 751, and its purpose was to get rid of those tests in the 60601-1 that would tend to shorten the useful life of the medical device and still do a good job of making sure that the medical device that was going to be plugged into the wall or operated on electricity would still be safe for use, even with our most vulnerable patients. That would be patients with catheters going right into the heart and things like that. So this standard, the tests are shorter. There are fewer steps in the test, and the testing limits are very close, very similar to the IEC 60601-1, but there are 3 different testing methods, and we have to choose which one we're going to use. So how do we do that? Well, in the standard, there is this decision tree. And this decision tree, or flow chart, if you will, helps us make the decision about which of the 3 testing methodologies is the right one to use for the particular brand and model of medical device or category of medical device. So there are 3. They are direct, differential, and alternative. And the one that is most like the IEC 60601-1 is the direct method. So you would be right to choose the direct method, except when the medical device has no on-off switch. That means that when you plug it into the wall, it is automatically on. There's no off button. So in that case, we're required to use the alternative methodology. So we're not going to go into deep dive on this decision tree and how to use it right now, but I want you to know this comes directly from the standard. And we do have a webinar in which we actually go step by step through this decision tree. And I suggest that you look for it and that you listen through the explanation. All right, we talked about IEC 61010 already. It's a intended for the clinical laboratory equipment manufacturer. It is for the installers of that equipment in the hospital or the clinic or the freestanding clinical laboratory. And once that installation has been done and documented using the IEC 61010, and the equipment goes live, that is, begins to be used, from that moment on, we will do repeat testing using IEC 62353. So the 61010 only applies to the medical device or the clinical laboratory equipment manufacturer and their installers. That's all. So unless you're working in that part of medical devices, then you would simply use the IEC 62353. Well, what happens if you have, like you'll note, we have 2 or 3 electrical safety analyzers that we sell that only have 5 lead posts across the top. And so the question is, well, what if I'm testing a defibrillator, or what if I'm testing a 12 lead EKG cart that has 10 ECG leads? Now what do I do? Well, we're allowed under the standard to short together all of a patient connection type, which would be like a B, like a temperature lead, a BF or CF, which could be ECG leads and other leads. And so we provide this 1 to 10 adapter that allows you to short together things like the 10 leads coming from the bigger ECG cable from 12 lead carts as well as defibrillators. And then you still have some lead posts at the top that you can use for pads or paddles. And that if there were extra or separate pacing test leads, that you would be able to connect those as well and properly run the entire test, having made your connections just once. Okay, now you have to remember, everything we connect to this 1 to 10 adapter gets shorted together and treated as just one patient connection. And that comes off and connects to the top of the safety analyzer to those lead posts. So we don't run ECG simulations through this, all right, just so you're aware. But it is for electrical safety testing, and it's very handy. Oh, and one more thing. You could use more than one of these if you needed to on the same electrical safety analyzer and medical device to run tests according to what the need may be. So it's not just one, it could be several, depending on how many patient applied parts or different kinds of applied parts, B, BF, or CF, that we need to short together. All right, how about things that are permanently connected to mains power, or equipotentially grounded rooms where we, at least before we start using that room, have to show that there are no ground loops, and that the equipotential grounding actually causes all current flow to move to a dedicated ground that comes only into that room and nowhere else. So to do those kinds of tests, we need to use a mode of testing on our safety analyzers called point-to-point testing. And that means you will use the red and the black connections on the lower left front panel. And one of them is going to be a black test lead that's going to go to that equipotential ground or to an appropriate ground that's farther away from where you are that you need to do the testing. And you may need a second 50-foot test lead in order to even move around and get your test probe on the right testing points under certain circumstances. Point-to-point testing can be referenced to protective earth or ground, or sometimes on a permanently connected to mains power, you cannot break into that mains power connection. So you're going to get close even if you're not right on ground, and therefore your reference point will be the reference point you choose, and the measurement you make with the red test lead is going to be whatever that is, current or voltage, with respect to that test point, reference point that you chose, because you could not get on the ground. And that's the way you're going to do it. Point-to-point testing is the way to do it. We can measure volts, ohms, and microamperes or milliamperes using this mode of testing. Well, what about this transesophageal echocardiographic probe? This is kind of a really important situation, because this transducer, it's an ultrasound transducer, it's inserted down the esophagus of the patient, and it's going to take an ultrasound image of the heart from right behind the heart. And so what you need to know is right behind the transducer face is between 400 and 800 volts of push, electromotive force. And all we need is just a little bit of resistance in order for that electromotive force to develop a current that would overwhelm the very, very tiny currents in the heart. And so we don't want to risk that. So as a result, we need to make specific kinds of patient connection or applied part tests on this TEE transducer. Moreover, the standard of care requires that these TEE transducers be cleaned and disinfected between each and every patient. And so that's done either in a tub, like you see on the picture on the right, a basin that has disinfectant solution in it. And in this case, the disinfectant solution is conductive, but we need to make sure it is sufficiently conductive for the test to be run. Now, in the little insert picture in this slide, you'll see a different tester. This is called the ULT800. It is designed specifically for less technical people that work in central processing where this cleaning happens. And so because there are um, no big graphic displays on the ULT800, it is simply a pass-fail device. It is also a battery-powered test instrument. So we run a mains on applied part test-ish, which means the battery is providing the push, but it's only got 12 volts. So even if the cleaning technician put their hands in the cleaning solution while we're running this test, they wouldn't be harmed. They might feel it, but they wouldn't be harmed. So that's why we produce this. Now, if the test fails, because the test limits are built into the ULT800, if the test fails for electrical leakage, then their job is to call a biomed, either from their own hospital biomeds or whoever's providing biomed services, and the biomed brings the regular electrical safety analyzer that they use. In this case, we're showing an ESA 615, and we're showing we're going to connect this in place of the ULT, but the ULT connectors need a little bit of a pigtail adapter here. So we use one pigtail adapter on the test lead, and we use the other pigtail adapter on the transducer adapter accessory that's appropriate for the particular brand and model of transducer that's being tested and cleaned. And that's how we run this test. So when it's run on ULT, the leakage current values are going to be much, much lower than they would be, well, in any case, whether it's ULT or the electrical safety analyzer, the leakage current values are much lower here than they would be if we had that transducer connected to its diagnostic ultrasound system and we ran the mains on applied part test through the whole system. That leakage current value will be a bit higher than it would be in the cleaning solution basin. There are two other ways that these disinfections happen. There are some tubes that hang on the wall that get filled with the same cleaning solution, and there are what looks like washing machines, but they are used to clean not only TEE transducers, but also endoscopes. And so it's a very important cleaning device. And once again, we would simply use the disinfectant solution as part of our testing circuit in order to run these tests. I hope that explains it a little bit for you. If you need more information than that, please let us know because I know this is a little bit more difficult to understand. And
Hey,
that's,
Jerry,
yes, ma'am.
before we move on, are there any videos relating to the testing ultrasound
There,
transducers?
in fact, there is one. Our other friend, Justin Ross, did one, and Edna, I think you provided a link out to that. Is that right?
That's correct. And that link is included in the chat. The video is available on YouTube. And so you're welcome to copy the link that's included. When you click on the chat, it's a HTTPS YouTube link, which will give you additional information relating to that subject.
I do want to say, be careful what you watch on YouTube. If you go to the Fluke Biomedical channel on YouTube, you get mostly what we produce. But every so often, you know how YouTube is, they'll sneak in videos that were made by somebody else. They're not us, and they may or may not have the right information. So please be careful. Follow our links. You better even yet go to our website, flukebiomedical.com, the Knowledge Center, and select videos. Okay,
Wonderful.
I
Mhm.
think, before we go to the Q&A, I just want to say there's much more to learn, and many of you are already registered for access to our Advantage Training Center, where you will find an entire course series on introducing what is medical device quality assurance, and then a whole nother course series on introduction to using each of our test tools that we've launched since 2004. So very useful stuff in addition to the video library, in addition to the recorded webinars and application notes, and there's even frequently asked questions by product. And these are all there for free for you to use, to get to know how to use test equipment you buy from us and to get to do your job better. That's what they're there for. So I encourage you to make sure you're using all of these as part of your learning and keeping current as a great biomed engineer or technician professional. All right, so let's go to the Q&A.
Hey, Jerry, can you hear me?
Yes.
Okay, great. We got a number of really great questions, so thanks everybody for submitting your questions. The first one, I think it'll be a pretty quick one, but it's related to the touch current slide that you were showing. And the question that they were asking is, can you explain why you use the aluminum foil?
Yes, because you have to complete the capacitor. You have to have a test point. And because there is none, there's no conductive test point that is not grounded available to you, you use that aluminum foil to create the test point. It is a capacitively coupled current flow, but it will happen in real life whenever the patient touches the medical device or whenever the nurse or doctor touches that medical device and touches the patient. That current will flow. When we're doing the testing, we must know how much, where is it flowing, and under what conditions.
Great, thanks for that explanation. The next question that came in was, how can I use an ESA to test the conductivity of the cleaning solution when testing ultrasound transducers?
You actually cannot use a regular ESA. The only test instrument that we make that allows you to test conductivity of the cleaning solution is the ULT 800, and it is a pass-fail test. So you're not going to get any measurement values for conductivity or anything like that. It is a simple test. It's just designed to make sure that the cleaning solution has not been too diluted, that has been mixed properly, and therefore is able to carry the current flow and be part of our testing circuit.
Great. And there was a couple questions around the IEC. If you could maybe just explain a little bit more about what that means and how it should be interpreted.
So the International Electrotechnical Commission, IEC, is the international body who actually publishes and is responsible for maintaining the minimum performance and safety standards for all medical devices. And they are housed underneath this umbrella called IEC 60601. All right, so if I just say IEC 60601, I'm talking about the umbrella. All right, I'm not talking about the electrical safety unless I say IEC 60601-1 or IEC 62353 or IEC 61010. Okay, that's the organizational structure.
Okay, next question. How do you test the electrical safety for medical device class 1 devices, but if you're unable to find the ground point on the surface of the machine?
You cannot. Here's the test that you cannot do if there's no accessible protective earth or ground. Even if you have a 3-prong power cord, you're not supposed to go get a ground from someplace else. The ground has to be provided on the medical device. So the test that you cannot do if there's no protective earth ground testing point is you cannot do any resistance, ground wire resistance. You cannot do any leakage current to ground, and you cannot do any applied part leakage to ground. Cannot. So those tests you will have to mark not applicable or not available because there is no ground pin. All right, there's no reference point. But even without being able to do those, you can and you must do the touch current test.
Next question is, how do you measure protective earth?
How do you measure it? Well, it's an ohmic, it's a resistance measurement. There isn't any, we're not doing like an electrician's test where you're testing the ground, that the ground is actually appropriately conductive all the way to where a conductive rod is driven into the earth. That's not the testing we're doing. We're not doing in what they call in Europe installation testing. That's not the biomed's job. That's the electrician's job. What we're testing is what is the resistance of the protective earth pathways that should be the lowest possible resistance value of anything, any conductive pathway on the medical device. And it has to be, depending on which standard we're talking about, it cannot be more than 0.3 or 0.2 or 0.3 ohms, 200 or 300 milliohms. That's all. If it's higher than that, then there's a problem that has to be corrected before you can do the further test, and before that medical device should be put into clinical use.
Great. Just a few more questions here. How do I do electrical safety in an isolated power location?
Oh, that's a great question. This question has been coming up, and finally, the auditors and the standards committees have provided advice about isolated power. So where are we talking about in the hospital that has isolated power? We're talking about the operating room. We may be talking about some ICU rooms or some ER treatment areas, mostly. That's what we're talking about. And the isolation is provided by line isolation transformers and line isolation monitors. We're not testing that line isolation system. What we're saying, the question is, how do I test a medical device that plugs in with a 3-prong plug or a 2-prong plug for electrical leakage inside an isolated power room? The advice of the standards committees is you shouldn't test to anything in that room, because all of what you think is a ground in that room is not connected to protective earth. It is connected to the secondary of the transformer, of the isolation transformer. And therefore you are missing some leakage current, and you need to know the worst case. You need to see all of the leakage current, which you cannot do inside the isolation. Therefore, the advice is this: if the medical device can be removed from the room temporarily, you bring it out of the room, plug it into a grounded mains power receptacle, and run the test. If the medical device cannot be removed from the room, it is mounted on a pendant hanging from the ceiling or something like that, or it is a robot that's permanently connected to mains inside the room or something like that, then you bring, not the permanently connected to mains, but anything else that you cannot bring out of the room, you will bring a very long drop cord or extension cord into the room, single connection point, and that will be connected outside the isolation to a grounded mains receptacle. And you will power your medical devices that cannot come out of the room from that drop cord. That's the advice of the standards committee, and that's what we should do.
Okay, great. As it relates to 61010, does it have to be done in every electrical safety testing schedule?
Absolutely not. It is done, as I said, by the manufacturer in their final assembly test and design validation testing. And it is done by the installer when the clinical laboratory equipment is installed in the hospital clinical lab or in the freestanding clinical laboratory. And then from that point forward, we use IEC 62353 for routine testing.
Okay. How do you conduct electrical safety testing using a multimeter? And they gave the example using the Fluke 289.
Okay, so not advised. The Fluke 289 is an industrial multimeter, and therefore you would have to improvise the appropriate test load. And that is prescribed in the International Electrical Safety Standards, and you shouldn't try and invent that or improvise that yourself. Use a safety analyzer. They're specially designed specifically for the purpose, and then you don't, if you want to go be a design engineer, go do that. But if you're going to be a hospital-based biomed or field service engineer, your job is to test what you have using the appropriate test equipment. Yeah, I'm not saying you can't, you can, but now you're bearing more responsibility than you should, because did you improvise that test load correctly? Are you doing the test exactly in compliance with the testing methodology prescribed in the international standard? My guess is you're going to miss.
Okay, thanks. Two more questions. So how does IEC 60601-1 shorten the life of the medical device?
It's another good question. So the IEC 60601-1 requires that the protective earth resistance be measured using 25 amps of current flow. And the reason for that is because the mains receptacles tend to build up carbon over time, and it's worse in 50 hertz 240 volt world than it is in 120 60 hertz world here in the US, but it happens. And so the 25 amp current is designed to clear the carbon that builds up on the leaves where your prong of your plug goes in and should stay tightly connected. So that carbon otherwise will cause your resistance value to be too high. And so by clearing it with the 25 amps for a specified duration of time, you will see that you may even see a higher resistance value, and you'll see it come down and fall within the testing limits when you actually do that test. But it's only required by the manufacturer at their design validation testing and their final assembly testing. We rarely use it during incoming inspection, and after that we should be using IEC 62353. The other test that tends to shorten the life of the useful life of the medical device is the mains unapplied part test. So this is testing the isolation barriers that protect the patient by isolating them from ground. And these are optical circuits or the like that are part of the BF and CF ECG lead wire connections. And so this mains mains unapplied part, means that we're going to apply 110% of whatever our mains power is on those patient connections across the top of our electrical safety analyzer for a specific period of time to measure the amount of leakage current that's there, and therefore evaluate the isolation barriers to make sure that they're protecting the patient adequately. That will shorten the useful life of the medical device over time. Therefore, 62353.
Okay. And final question, how do I do insulation resistance test with the ESA 612? How are the connections made?
612, 614, and 615. When we do the insulation test, this is the test with the Megome button. It is a resistance test. And what we're looking for is the quality of the insulation around each of the conductors in our power cord and in our patient connections. And so we're going to apply, you have a choice here of either applying 250 volts DC or 500 volts DC on those connections to verify the quality of the insulation to make sure it's sufficiently resistant. And so we're looking for measurements in megohms, all right? And that's what we're looking for. It is a very different test than the mains on applied part isolation test, completely different test for a different purpose. But there's instructions in our user manuals about how to connect that up and how to run that test. By the way, the insulation test is only required to be done if the manufacturer of the medical device says that it must be done in the service manual test procedure, or if the local national standard requires that it be done because the IEC standards do not require it.
Wow, Jerry, thank you so very much. A wealth of information and my wonderful questions from the audience. Thank you both. We are at time now.